All right, we are in chapter 2-3. This is the last section of chapter 2, and this is recording number 1. Other types of graphs. Okay, so there's a whole boatload of different graphs. He's going to talk about a couple of them here. Okay, I think it's pretty straightforward. I hope it is. As I mentioned in my announcement, and I think in my syllabus, but certainly in the announcements on Canvas, if you have any questions, just send me a question. I'm happy to answer your questions. Either make an appointment to talk to you, or I'll send you an email response, or I'll make a video and I'll post the video. Believe me, if you have a question, other people have a question. Okie dokie. So we got other types of graphs that are used. This kind of looks almost like a sideways histogram, doesn't it? Okay, so I'll take a look at all these different things. This is what we often call a pie chart. Okay, this is one that's very strange. This so-called dot plot is kind of weird. Okay, so let's take a look at a couple of these. Okay, so the first one is a bar graph. We'll look at the bar graph. It represents the data. You use vertical or horizontal heights. So how is this any different from a histogram then? I think it's different from a histogram in that, remember when we were talking about a histogram, we said that these guys had to be contiguous. Well, now these don't have to be contiguous. There's no real connection between the shoes and the clothing and the dorm decor. There's no reason for them to be next to each other. It's not like they're just sub-intervals of a temperature, for example. It's not like they're ages or something. These are totally different categories. So we can just as easily have them not contiguous. If they're not contiguous, if they don't overlap at all, then we would say they're disjoint. Something is disjoint in math means that there's no overlap whatsoever. The sets are considered disjoints. Here the categories are disjoint. Shoes are not the same as clothing. Clothing is not the same as decor, and so forth. And again, we just draw plot the points, draw the rectangles. Now on here, the other thing that's different is that on this bar graph, we're okay to have horizontal, the data going horizontal. So the categories are the same as before, electronics, dorm decor, and so forth. But now instead of going up, now it goes this way. So the x-axis is now the amounts or the frequencies or the prices or what have you. Okay, so I'll let you read that. I'm sure you'll be able to get through that. Okay. This is a compound bar graph, compares 1 year to the next as an example. So here we go. Or here it is in gender. So we're talking about 1960, 1980, 2000. We're talking about men and we're talking about women. Then this right here, the y-axis, that's the actual data itself. That's the data values, I should say. So we're talking about, in this particular case, we're talking about never married, I guess. Is that what it's talking about? Yeah, never married. So people that have never been married. So if you've been married and now you're divorced, you're not in this category. Never married means never married. Okay, so the men are in this color, the women are this color, and as you can see, as time goes on, it's getting more and more people are never married. As time goes on, you might look at this, you say, I don't know what else you could say. But at least you can look at it and get some idea of what the numbers are. Okay. Clearly, as time goes on, you're getting more and more people that are never married. Now, if I may, just as a side note here, as an editorial comment, this is an example of how the actual numbers are not really as important as the relative frequency. Now, do you see why? I mean, okay, sure, as time goes on, the number of people is going up, but the population is going up too. The population of age, people that are old enough to be married is going up. So for all I know, I don't know if this is true or not, but I'm just saying, as an example, it could be that the percentage, the relative frequency, their proportion, those are all terms that basically mean the same thing. The percentage of people that have never been married is exactly the same from the year 1960 to the year 2010. For all I know, it's 10% of the population. But obviously, because the population has been going up, the numbers, the actual numbers of people has also gone up. But if you plotted this by way of percentages, it'd be a flat curve. It doesn't go up at all. So there's an example of where relative frequency sometimes means a lot more than the actual numbers. Okay, all right. Pareto chart is for categorical variables, and you order them from, you arrange them in order from highest to lowest. Okay, so we got all these various things here. We plot the points, boom, we go down. Okay, so again, they're vertical rectangles. They're rectangles. Frequency distribution doesn't say they have to be disjoint or contiguous. The way he drew it right here is they're contiguous. There's no reason for them to be contiguous, right? You could have Washington, then you could have a little bit of space, then you could have New York, then you could have Boston, a little more space in between them. I mean, there's no reason why you wouldn't. Okay, it's just a matter of making the charts look nice, you know. So a time series, that's what you get. You see this all the time in the current situation. As time goes on, the number of people that have died goes up. As time goes on, the number of people that whatever happens goes up, okay, or goes down, whichever. Okay, all right. So again, you're just plotting data in order to make it mean something more. If you just looked at this, it'd be pretty hard to really draw any good conclusions. You look at this and you could sell somebody something. So if you're trying to sell somebody something, either or persuade them about something, typically you're going to want your information to be in some kind of a graph. Okay. All right. So I think this is hopefully I'm helping you here, but this is very, very straightforward. A pie graph. Don't look me in the eye and tell me you've never seen one of these. Okay. These are just, it's like a pie, it's like a pizza pie, and what percentage of each one. So in this particular case, we're talking about snacks, but it could be anything, right? It could be cars, it could be people at certain age groups, people that, what causes of death, you know, pneumonia, the flu, getting run over by a beer truck, whatever it happens to be, those percentages can go into this pie chart. Obviously, the percentages have to add up to be 100%, to say the least. The only thing I can see here that might kind of drive you nuts is how do you get these percentages? Well, it's always going to be the same thing. It's going to be F over N. F is the frequency. How often does it happen? What's the actual number of, what are we talking about here? Snacks. The number of snacks. Okay, 11.2 million. Tortillas is 8.2 million. And the bottom here is 30 million. So what percentage is potato chips? 11.2 divided by 30, F over N, because that gives you a percentage, right? Or I'm sorry, that gives you a fraction. Okay, so 11.2 over 30. What is that? Let me just. Okay, I got my little handy dandy calculator out. 11.2. That's the number of potato chips that were sold, divided by 30. That's the total number. So 11.2 million divided by 30. What do you get? You get 0.373. Okay, so it's 0.373, a little more than a third of all of the chips, or of all the snacks, excuse me. So a little over a third of all of the snacks were potato chips. Well, again, it's a little bit harder to see that, you know, to analyze or to think about that without having it in a chart. So if I want to have it in a pie chart, I need it to be in percentages. So I multiply it. If I want it to be in a pie chart, I want it to be in percentages as depicted by what percentage of the chart is popcorn. What percentage of the chart is tortilla chips? Well, the easiest way of doing that, since it's in a circle, is to do it by degrees. So when you get the fractional part, when you get the, you know, what's the relative frequency, you don't multiply it by 100. That would give you the the percentage. Well, actually, he does here. He multiplies it by 100. That gives you the percentage. So potato chips is 11.2 million divided by 30 million. that gives you 0.373. Multiply it by 100, that gives you 37.3%. Okay, so that's the percent. But how are you going to put that percent into a pie graph? You need degrees, right? So if you need degrees, you take this 11.2 divided by 30 and you multiply it by 360 degrees, because there's 360 degrees in that circle. So this is the fractional part of the circle that belongs to potato chips. So that's 0.373 times 360 degrees. That gives you 134 degrees, roughly speaking. He did some round off, okay? So it's very, very straightforward, I think, but you got to do a couple of them. And this is a perfect example of why I don't like doing electronic homework or online homework. I think you need to do this by hand. You need to write this out. There's something magic about doing it by hand. It helps you learn it. And then when you send it in to me, send me your work, I'll help you along and criticize you and, say, hey, you need to be more clear here, or you made a mistake here, or whatever. I'll do my best to do that. Okay. So in any event, you get the percentages, but then that corresponds to what's the degrees. Okay. So between this part of the pie, it is a certain number of degrees. Well, what's the number of degrees? The number of degrees for potato chips is 134 degrees. Okay, where's the potato chips? Right there. So this angle right here between here and here is 134 degrees. You got your protractor out, you see what I'm saying. Now, do you remember that from another class, perhaps? 180 degrees is half of this circle. So 134 degrees isn't quite half. It's significantly less than half, okay? Let's see. How about this one here? Popcorn is 46 degrees. Popcorn is 46 degrees right there, okay? That looks about right to me. That's 46 degrees is right around 45 degrees. 45 degrees is half of 90 degrees. Right there, that's a right angle. That looks like about 90 degrees to me. So this is about half of the 90 degrees. So it looks about right, okay? Nobody does this by hand, okay? You do it by hand to learn it. But after you do it a couple of times, then you use the software and you just plug it into, there's a bazillion websites out there that you just plug in the data and it will draw these graphs for you, okay? All right, here's another example. Again, it's the same exact thing. I'm telling you, the best way to learn this is do the examples, pencil and paper in hand, or pen and paper in hand, crank these out, and it becomes abundantly clear. The only one that I think is a little weird here is these dot plots, okay? The dot plots. What the heck is a dot plot? It's a statistical graph. It's a way of depicting the data. Each data value is plotted as a point above the horizontal axis. So how weird is that? So here we go. The named storms, okay, for the last 40 years. In this year, we had 19 of them. This year, we had 9 of them. This year, we had 16. The idea behind a named storm is the federal government, some division of the federal government, they name the storm so that everybody can say, okay, this is Hurricane Katrina, this is Hurricane whatever, and they go in alphabetical order. That's how they do it. Okay, so for the until civilization collapses, we will know which storm we're talking about because it has a unique name. So if it's a named storm, it goes in this list here, this table. And it has to be meet certain requirements to become a named storm. So that's the background story. Okay, so once you do that, well, look, you've got these data values. How many times were there 10 of them? 1, 2 times. Well, you look up here. Here's one. Where the heck's the other? I'm running out of time, so naturally now I can't find it. Okay, here's one. This year had 10, and this year had 10. How many years? So boom, boom, there's 2 of them, okay? So that's the concept there, okay? Stem and leaf plots, darn it, I'm running out of time. Okay, you have this data, you arrange it in order, okay? You arrange it in order, okay? It's a little bit cumbersome if it's a large data set, but then you separate it according to the first digit. So like 0, 2, that's 2. 1, 3, 1, 4, that's 13, 14. 20, 23, 25, it's all organized, right? Then you do this, 0, 1, 2, 3, 4, 5, and then across here, you put in that second digit. So 2, 0, 2, 3, 2, 5, that corresponds to 20, 23, and 25, okay? 3, 1, 3, 2, and so forth. So it's 31, 32, 32, 32, 32, 33, 36. Boom, there it is, okay? Is this of any particular value? Not so much. All right, that's the end of this tape. All right, that's the end of this recording.